Okay, we'd like to get started. At this, we're projected to go on here until about 2:30 in the morning is my projection at the moment. So sooner we get started, the closer to 2:30 we'll finish. The first talk, this series of talks will be 7 minutes each. I will set the timer for 5 minutes. The first talk is by Professor Anderson, Resonating Valence Bonds, a new mechanism for superconductivity.
Can you hear me? Is that okay? First, I want, of course, to talk about collaborators. The original ideas here were my own, but then we very rapidly began to work with I very rapidly began to work with G. Bhaskaran of Princeton and Zozo. Some very interesting further ideas have been added by the Santa Barbarians, Steve Kivelson, Jim Sethna, Dan Rockshar, who were all at Santa Barbara together. I'm going to start this talk absolutely backwards for a theoretical talk. Namely, I'm going to start talking about the experiments I can explain, because I certainly won't have time to tell you.
Phil, could you raise the view graph a little bit? People are having trouble in the back.
Okay. Well, we're not looking at that yet.
Oh, all right.
I want to talk about the many experiments, or a number of experiments that we think we have fairly unique explanations for, experimental facts. And I have the impression that most other theories are kind of stuck with one experimental fact. I'm going to be a little bit honest with you, however, and say that I'm not sure that I can explain all these facts at the same time, since we have a number of different versions of the theory. But certainly all of them are available within various aspects of this theory. The first thing, of course, we can explain is why this particular kind of oxide, and in fact why the theory started from this kind of oxide, and we can explain why also barium bismuth oxide is an interesting material, and why lithium titanate is an interesting material, using very similar ideas. We can explain, or we can at least discuss reasonably, the nature of this very strange crystallographic phase transition above room temperature in the insulating material, or in the semiconducting material. We'll call it from now on the Twitch transition, because it's such a very strange crystallographic object. And also we have some ideas on the nature of the Hall effect, as measured by Ong, and actually I see by some of the other data very similar results from other groups. We think we know why there is, the one thing we are sure of is why there are high TCs, basically because it's some number, not too far from 1 times an exchange integral instead of a phonon frequency, and because we do not have to contend with the strong electron-electron repulsion that other theories have to worry about. The very peculiar normal state resistivity, which I'm going to show you shortly, that actually Bertram Batlogg already commented on. And finally, some very peculiar tunneling data. Of course, there is a great deal of tunneling data, and all of it is very peculiar, I assure you. You have to guess which piece of this tunneling data you're really going to take seriously. And I'm making a particular choice here. But it is true that all of the tunneling data indicates some very anomalous behavior. The Twitch transition, I don't want to really emphasize too much. I just did want to call your attention to the data that various groups have had, and in particular Ong at Princeton, since I'm here representing Princeton. There is this strange orthogonal to tetragonal phase transition, which occurs in some samples, most samples, and in the undoped state, and reducing as you go to more dopey states. And the transition does not change any bond distances and doesn't change seriously any lanthanum oxygen bond or any copper oxygen bond angles. All it does is do an alternate twist of what we in our theory call the red coppers and the black coppers, the red coppers being turned to the right, say, and the black coppers to the left as you look along one of the diagonals in the basal plane. This transition is so small and has so little to do with what you presume to be the actual electronic parameters. It can't possibly change the electronic parameters enough to introduce the large gaps, but it seems to. It seems, however, to change the Hall effect radically so that there is very large electronic effects of this transition. I better accelerate. The peculiar resistance that I referred to is this strange fact that the resistance seems, when you get a good sample of any of these materials, the resistance seems to extrapolate to zero. As I was looking at the data from various other people, I was finding that I wasn't sure what this power law was, but I was always sure that it extrapolated to zero when I got a good sample. And that's a very strange thing. Think about that. What has a zero resistance at t equals 0 when it is so darned impure? It is extremely impure. It is extremely random. And finally, some very fascinating data. Aaron Kapitolnik, I say Jabal, Quaid, and all, but in fact the work, or the staying up all night, is mostly Kapitolnik. He showed us this curve, which really, he will show later, really is pretty spectacular. dIdV versus V looks like a second derivative curve at the very least, maybe stronger, maybe pointier than that. And you have these strange delta functions at numbers delta, 3 delta, and 5 delta, and a plateau. The 3 delta and 5 delta can be artifacts. The 1 delta and a delta function cannot be, as far as I know. Let me talk then just what basic idea we're going to use for this. The physics is, the basic RVB idea was invented in 1973 in response to some old ideas of Pauling's. And the idea of the resonating valence bond is that the physics is in the insulating state, that there are a whole sequence of very strange insulators. This one isn't because it doesn't exist. It probably would be if you could make it. Lanthanum copper oxide and barium bismuth oxide. This one is a semiconductor when you make it pure. Barium bismuth oxide is a very good insulator. And there are a number of other substances which have this strange property. Whereas what is very noticeable is the rarity of honest-to-goodness antiferromagnets made with spin-and-a-half ions like copper. There are various ideas that have been proposed to explain these having gaps. None of them really wash very well. So we suggested that they are not, and they are all pretty clearly not antiferromagnetic, or not antiferromagnetic enough to explain the gap. So we suggested this very strange state, which is an insulating liquid, an insulating fluid of pair bonds between the different atoms. In other words, of singlet pairs made up of spins on the different atoms. We put one electron per atom. We keep 1 electron per atom to make it an insulator. But then we allow the spins to move around at will as though they were binding themselves together, or they are binding themselves together in singlet pairs. And the reason why this is an energetically sensible thing is that you get 3 times as much energy for spin-a-half from a bound pair as you do from an oppositely oriented pair. And you gain a lot of resonance energy, and you may gain some virtual spin parallels energy. And the relevant exchange integral is about 500 to 1,000 degrees K. The basic idea is that with doping, the resonating valence bond theory does not, our field system does not break up, but instead the charge carriers are solitons within this, various kinds of solitons within this resonating valence bond liquid, and these solitons can be charged holes, or they can be spin excitations, and or they can be pairs of charged holes, and so on. And there are quite a number of excitations of these. Now, from that, I'm going to go just finish up with one sentence. The one sentence is, you can do a zeroth order treatment of this resonating valence bond theory, and that was done by Basker and Zoe and myself. And that does a very strange thing. That gives you a Fermi gas without any charge transport in the insulating case. And the charge transport only occurs when you dope it. And that then gives you Pauli susceptibility and a linear specific heat in a semiconducting material. Oddly enough, although we're a little dubious about why it occurs, that is the behavior of lanthanum copper oxide. And that was the first point at which I really began to think that we were beginning to make some sense. The second sentence is that you can, okay, and one more sentence. You can, however, by various tricks, open up a gap in this strange Fermi liquid, and that is the state that Kivelson and et al. Are trying to work with. If there is a gap, then you get a very strange soliton, which is a boson of charge E, and you can boson-condense these bosons of charge E. I didn't take that too seriously until I realized that that explains the resistivity data. If your transition temperature were a point at which a boson gas decondensed, where it was the melting point of a boson condensation, the bosons have not under impurity scattering, have not temperature-independent conductivity, but various, depending on their spectrum, various conductivity laws with temperature, all of which extrapolate to 0 as you go to t equals 0. Thank you.
Thank you, Phil. Thank you very much, Phil. The next talk is phonon softening and 2D plasmon exchange as a mechanism of high transition temperature superconductivity by Dr. Kresin.
Okay, we have the following key question. What makes this high TC material unique relative to hundreds of other superconductors? These materials has two prominent features. First of all, they contain two-dimensional electron system. And secondly, they contain subgroup of electronic states with high density of states. Based on these two features, without any additional assumption, one can show theoretically that two major conclusions follow. First of all, we have phonon softening, and as a result, strong electron-phonon coupling. And secondly, we have appearance of a non-phonon mechanism, namely exchange of two-dimensional plasmons. And this is two major mechanisms. Number one, strong electron-phonon coupling. Softening in two-dimensional case has been described in my previous paper. And main idea is that phonon softening, and as a result strong coupling, is a result of existence of nesting states on the Fermi curve. In two-dimensional case, we have Fermi curve, not Fermi surface. Now I'd like to show you expression which can be obtained directly from the Eliashberg equation, which describes critical temperature for any strength of electron-phonon coupling. All limiting cases, small lambda and intermediate lambda and very strong lambda, can be obtained from this expression, but this expression describes general case of any lambda. Now, major manifestation of strong coupling is that energy gap divided by Tc, this ratio, must be larger than BCS value. As a result, only one can show from a Eliashberg equation that behavior of this ratio as a function of lambda is following. From BCS, we have increase, and when we have saturation, near some number approximately 14.5. So, and this is real manifestation of a strong electron-phonon coupling. Both of these results will be discussed in more detail tomorrow during regular morning session, which probably will be kind of transition of our meeting. Now, speaking of plasmon mechanism, I'd like to show that in two-dimensional case, we have picture which is entirely different from 3D case. Two-dimensional plasmon branch can provide, in addition to the usual phonon branch, additional electron-electron attraction via exchange of two-dimensional plasmons. Particularly is important short wave region. So wavelength is shorter than interlayer distance, so we still have two-dimensional plasmons contribution. And also it's important that the case of small electron concentration is very favorable for this plasmon mechanism. Now, I'd like to suggest experiment, some independent experiments are needed to detect the presence of a plasmon mechanism. First experiment is tunneling spectroscopy, which is, as known, displays all peaks, including plasmon peak. And second, neutron scattering, which affect the phonon subsystem only. By comparison two sets of data, one can establish the presence of a non-phonon plasmon mechanism. And I think it will be very exciting because, as far as I know, it will be first direct observation of a non-phonon mechanism superconductivity. So, as a result, we have coexistence of two factors. Major factor is strong electron-phonon interaction. That's major mechanism. But in addition, we have additional increase of Tc by two-dimensional plasmon exchange. This is expression for critical temperature in the presence of both these factors. It's obtained by kind of general Eliashberg equation. So here Tc phonon is this expression is critical temperature due to usual electron-phonon mechanism. And now you can see from these reasonable numerical examples that even plasmon coupling constant is relatively small, it can provide noticeable increase of critical temperature because of large predexponential factor. Okay, now I'd like to give summary. So, low dimensionality in the presence of electronic states with high density of states results in the coexistence of two following factors. Major factor is phonon softening, and as a result, strong electron-phonon coupling. And second, two-dimensional plasmon mechanism. Both of them made this difference we know, and they provide high Tc superconductivity in these materials. Thank you.
Thank you very much. The next talk is Van Hove singularity, breathing modes, resonant charge fluctuations, and high Tc in perovskite superconductors. Professor Freeman will give this contribution.
Thank you very much for this opportunity. Is this on? It's backwards. Close to that.
Not too close. Okay, try that.
No, it's still not. Oh, yeah. I want to thank Bednorz and Muller and Paul Chu for giving me an awful lot of fun for the last 3 months. It's certainly been the most joyous period of my life in physics. Today I'd like to share with you some of that joy and some of the information we've gotten on these high TC perovskites. I'll show you results for lanthanum copper oxide and also for the new superconductor, the yttrium barium copper oxide. The work was done with my collaborators, Yu, Fu, Masita, Shu, and Watson-Yang. I'll talk about highly precise FLAPW total energy approach. I'll talk about bands, bonds, frozen phonons, charge fluctuations. I'd like to get to the mechanism of superconductivity. And what I really want to share are results, insights, and I think understanding. To begin with, here's the band structure that you heard about for lanthanum copper oxide. What you see at the arrows, well, first of all, there's a single band crosses the Fermi energy. This is a copper oxygen band. Its width is 3 volts. It's very substantial. The overall width of the band is 9 volts. There's considerable Fermi surface nesting indicated by the arrows. It gives rise to a peak in the generalized susceptibility, which I can show you. It leads to a soft phonon mode for the x equals 0. That's the composition without the divalent atoms. There's a body-centered tetragonal to orthorhombic phase transition, and that shows that it goes from being a metal to a semiconductor. In the band structure, there's a very important feature which is shown here. That's the Van Hove singularity. I call it an SPS. That gives rise to an awful lot of physics. It immediately gives rise to a Lifshitz-type transition. This is the Fermi surface for x equal to 0. It's a whole surface around this point. Look quickly, and you'll see that it changes dramatically. It becomes electron surface. This is at the peak, x equal to about 0.16. Then it changes character as you go beyond. Now, the density of states, whet your appetite, shows this sort of a feature. Let me show you here the SPS. It's a little glitch on the density states curve. However, what it is, it's due to the Van Hove singularity. Here is Vesuvius rising out of the sea. Here's your free electron band. Okay? Here's this sharp singularity. X equals 0 is marked here. X equal to 0.16 is up there. And that's the point where the highest T sub C occurs. Then you come down and the superconductivity disappears at 0.3. If you look at the charge density, here is a vertical plane. Here's a state at the Fermi energy. Here are the copper-oxygen planes. You see the dx squared minus y squared orbital that Muller talked about, bonding with the p parallel. Notice no charge density in these states, in this region in between the planes. What you have is metallic sheets on the copper-oxygen planes. You have an insulator in between. The lanthanum shows no charge density distribution at all, so if you put a rare earth, there's no way the rare earth can really interact and with pair-breaking effects. We also did some frozen phonon calculations to see the effects of a breathing mode. This shows you on the left the in-plane charge density, the copper-oxygen. Now we let the oxygens move. These two go to oxygen 1. These two go to oxygen 1 there. You leave behind then, you get a charge fluctuation between this copper 1 and the copper 2. Okay? The copper 1 and copper 2 are oscillating in charge. It amounts to 0.3 of an electron volt. It's enormous. Here's the vertical state, okay, direction of the copper and the oxygens, and you see the splitting into 2 states, an occupied and an unoccupied. The deformation potential is large. We've calculated for the breathing mode, and what we find is a very unusual feature. For x equal to 0, here's that softening, here's that dip, okay, an attractive well that comes about. But as you raise x, it becomes a hard phonon. So instead of a soft phonon, as you increase x, you have a hard phonon. So it's strongly anharmonic for x equal to 0. Now look at about x equal to 0.15. The frequency is high frequency mode, 1100 Kelvin. That's due to the fact that the oxygens are so light. So let me tell you about some of the main results that we have for the lanthanum barium strontium copper oxide. It's quasi-two-dimensional metallic copper-oxygen planes, insulating lanthanum oxygen planes. The parallel coherence length is about 130 angstroms. The perpendicular one is only about 1 angstrom. HC2 parallel is 200 Tesla. Hg2 perpendicular is about 2 Tesla, enormous anisotropy. The Van Hoff saddle point singularity and the Fermi surface Lifshitz transition that I mentioned corresponds quite closely to the changes in T sub c. From the measured gamma and the calculated density of states, we get a lambda of about 0.3 plus or minus 0.3 with the experiments. There are anomalous thermodynamic effects, and so forth. Here's the optic breathing mode that I mentioned. Now, one of the things that we see very strongly are charge fluctuations. I said 3/10 of an electron. The chemical picture is clear. In the ground state, you have copper 3 plus and copper 2 plus, the mixed valence. The superconductivity goes beyond BCS description. You can look at the description by charge fluctuations, negative U centers with real space pairing, or bipolarons. These are just different mathematical descriptions of what we see going on. Here is the new superconductor. There is the phase worked out by Hazen et al. We have calculated the electronic band structure first for the yttrium copper oxide, the cubic type peroxide with a tetragonal distortion. I show you the spaghetti so you can see that we did it. Here is the spaghetti for this triple perovskite. Here is the density of states. Notice that we have a number of peaks here for the Van Hoff singularities. There are 3 copper planes in this structure. They act independently. Look at that Van Hoff singularity. Look now and look at the charge density distribution for the valence charge in a perpendicular plane. Here's that copper. In this plane, we call it a copper 2. The copper 1 is in the middle of 2 baryons on either side. The yttrium are down here, and the yttrium is up here. The yttrium copper distance is a lot shorter than the barium copper distance. And the oxygen vacancies occur in this plane, in the barium planes. So again, we're seeing the two-dimensionality effects. Here's a dominant state at the Fermi surface. Okay, here's a charge density for this state. Now, for a companion state, the other copper, you see, is absolutely orthogonal to it. So we have 2 states, 1 and 2. And I am just finished when I summarize my results. We have, again, a very similar result for this system as for the low temperature, the 40-degree low temperature superconductor. It's quasi-two-dimensional electronic structure. In this case, it's due to vacancies. In the lanthanum copper system, the two-dimensional structure was due to the fact that you had the anisotropy in the lattice constants between the C and the A. Metallic copper oxygen planes again. Insulating yttrium oxygen barium oxide planes. No pair breaking for magnetic rare earth substitutions like gadolinium, and I was only aware of the work of Fisk et al. At Los Alamos. Apparently others have also done it, as we heard tonight. The Van Hoff singularity gives on top of this low density of states, there is a small lambda from the gamma measurement that we had heard from Batlog et al. So now we expect the same mechanism as in lanthanum 2, M sub x, copper al4 for superconductivity, and it will take only one theory, a unified theory, to explain it all. Thank you very much.
Thank you, Art. The next paper is given by Dr. Papakonstantinopoulos, Theory of the Electronic and Superconducting Properties of Lanthanum M Copper Oxide.
You did? Yeah. Thank you. I don't think I'm going to attempt to show as many viewers as Dr. Freeman has managed to show. This is probably a record. However, I will first start with my collaborators, Warren Pickett and Larry Boyer from the Naval Research Laboratory, and Henry Krakauer from the College of William and Mary. What I will be telling you is that in these superconductors we have conventional superconductivity. We have a strong electron-phonon coupling operating. I will concentrate in the by now so-called low-temperature superconductors, that is lanthanum barium copper oxide system. However, I will make some perhaps semi-speculative remarks on the yttrium compounds. I will start with a similar picture like the one you saw just now about showing the body-centered tetragonal compound densities of states which were done with the linearized APW method using general potential. And what you can see here on the left is the lanthanum compound, and on the right, a compound in which we have replaced half of the lanthanums with barium. You see in this picture the decomposition of the density of states per sites, and I want to emphasize that most of the action comes from copper and oxygen, certainly at the Fermi level, but all these bands of bands are copper, oxygen in both cases. The other materials, like lanthanum, play a very passive role, and perhaps they serve in stabilizing the structure. We do find the same feature in the density of states, this little bump just below the Fermi level, which corresponds exactly to this 6.15 barium or strontium or calcium situation, which raises the transition temperature. We have taken the point of view that we can propose a model of the cubic perovskites as well in order to make a series of systematic studies. And we have seen that the cubic perovskite, which apparently it is the building block of all these layered compounds, has a band structure and density of states which is quite similar to the layered ones. And you can see here a set of densities of states for the cubic compounds. What I have marked here, it is where cesium would be. We have also done the band structure calculation for the compound in which we have replaced lanthanum by cesium, with the hope that the density of states at the Fermi level is going to be very high for that, and indeed it is, but the quantity which I'm going to be calculating in a minute for you, that is the electron-phonon coupling parameter, is really not changing very much from the lanthanum compound. The way we do our calculation of the electron-phonon coupling, it is by following Macmillan in writing the electron-phonon constant lambda as a product of an electronic term, as a ratio of an electronic term, eta, which is the so-called Ni squared, and a phononic term which contains an average of the phonon frequency. As I said before, there are practically no lanthanum states or barium states at the Fermi level, so the result is that this term is 0, and so we are left with two terms, the copper term and the oxygen term, which we can decouple in this way, given the fact that the mass of copper is about 4 times larger than the mass of oxygen. We calculate from first principles, from our band structure calculations, the numerator of these expressions using the rigid Maffentine theory of Gaspari-Geoffrey. And we make the additional assumption that the force constant of copper is equal to the force constant of oxygen, which gives us one adjustable parameter, the average phonon frequency of oxygen. We then use the Allen-Dines equation, and we determine the transition temperature Tc from that. And I will first show you a table which shows these eta, the numerators of the lambda expression. I wanted to first observe that we are talking about relatively low densities of states at the Fermi level, and we are also talking, in comparison with other well-known superconductors, like, say, niobium nitride or the A15s, of relatively low values of this parameter eta. To emphasize the point about the cubic structures, I have here the oxygen contributions to this parameter eta for both the layered compounds and the cubic ones, and you can see that the sum is just about the same. The remark I wanted to make about yttrium is when we did the cubic calculation for yttrium, and what you should be looking now is just leave this out and look at these two columns. You can see that the parameter eta for yttrium increases by quite a bit. Finally, I will show you the transition temperature as a function of our parameter omega, the average frequency of oxygen. And there are two things shown here. One, the transition temperature for x equals 0 in this compound and for x equals 0.15, and the corresponding lambdas. So if the phonon frequency is around, say, the value 200, then we get transition temperatures which are in the measured range of about 35 degrees. I will conclude emphasizing that we do propose an electron-phonon mechanism, electron-phonon interaction mechanism, but we require soft phonons for this to be accomplished. Neutron scattering experiments at NBS by Jim Ryan and his co-workers are in progress, and we hope that we'll be able to get these m omega square averages by analyzing those data. We have now started calculations using the coherent potential approximation, because don't forget that the calculations I have presented are calculations of stoichiometric materials. However, we all know that the real superconductors are alloys. So we want to incorporate in our calculations disorder, or between, say, lanthanum and barium, and also the effect of oxygen vacancies. Ron Cohen in our laboratory is using the potential-induced breathing model, which has been developed at NRL, and he's now calculating the phonon spectrum, and some preliminary results show soft phonons. Thank you very much.
Thank you. The next talk is theoretical efforts at AT&T Bell Laboratories to understand high TC superconductivity. This talk will be given by Dr. Schluter, Michael Schluter.
I'd like to discuss with you three particular theoretical efforts, namely electronic band structure calculations. Let me get this right here. Carried out on the 40-degree material by Len Mathis, and on the 90-degree material by Len Mathis and Don Hammond. And then two types of theories to explain superconductivity based on the findings of these electronic structure calculations. Let me start first by reminding you the structure of these materials, and in particular pointing out to you the relevant parts relevant for the electronic structure. We all know by now that in the 40-degree material, the relevant pieces come from copper-oxygen planes, shown here in red and green, which form a two-dimensional network of conducting atoms. The material is anisotropic in its appearance. The planes are separated rather far from each other. Now, in the 90-degree material, the skeleton of the donor atoms, I may call them, is surprisingly isotropic. It is a cubic perovskite phase, or almost cubic. However, this is misleading. The conducting pieces, again, are planes, as shown here, between the yttrium and the barium planes. And then, to a big surprise, a new element comes in, and this is the structural data of the Bell Labs group, a new element which is a one-dimensional chain. This one-dimensional chain is shown here, a copper atom, which again is fourfold coordinated, so it is very happy, but it is connected only in the x direction. And this is due to the fact that the vacancies, the oxygen vacancies, are sitting in this copper plane. And what I have assumed here, or what Len Mathis and Don Hammond have assumed here, is that they order, and therefore you have a one-dimensional conducting chain combined with two-dimensional sheets over here. And as we heard before, if one sheet is good, more may be better. But leaving this aside, here's the band structure for this 90-degree material carried out under these structural assumptions. it looks very complicated. However, the physics is rather simple. It can be summarized by remembering these sheets and chains. And what I show you here is the electronic structure due to those two-dimensional sheets. It is copper-oxygen bonding and antibonding pairs, the Fermi level intersecting the antibonding band. On top of this, now comes this one-dimensional chain, which gives these red bands. If the material is in the O7 form, then the Fermi level lies roughly in the midpoint of the two-dimensional band and at the lower end of the one-dimensional chain. I also like to remark, and this you have seen before, that the barium and yttrium atoms indeed are only donor atoms. They are far away from the action near the Fermi level. Now, if you look at the Fermi surface of this material, then you find a rather remarkable Fermi surface. The two-dimensional bands give you cylinder-type Fermi surfaces, but in addition to being cylinders, they are rectangular. They are rectangular, and this has remarkable properties. The same Fermi wave factor spans many pieces in K-space. In addition to this two-dimensional, this, by the way, results from those sheets. In addition to this feature, we have the chains. They, too, give rise to sheet-like Fermi surfaces, these chains, I mean, but they have a different K Fermi and a different spanning vector. So we have truly a superposition of two types of Fermi surfaces, and this can affect K-space in a much broader fashion than otherwise. As it was pointed out first by Len Mathis, there's only one mode in the system, or one type of mode, which couples to first order to the states at the Fermi level, and that is the breathing mode. Now here we have then two-dimensional breathing modes with the oxygens breathing in and out around the copper atoms. And in addition, we now have one-dimensional breathing modes along these chains. These would be the longitudinal modes, and transverse modes of oxygen atoms, these backbones of the chains moving up and down. Let me quickly summarize what the electronic structure then consists of. These are the relevant points. It is rather remarkable. It's almost a chemical accident, I would say, a singular accident, that copper and oxygen ionization potentials in these ionization states that we have here line up. Since they line up, we can form, in the band structure picture anyway, broad bands. We have broad 5 to 9 eV wide copper-oxygen bands, and the Fermi level cuts through the antibonding part of these bands. So we have metallic copper-oxygen states at EF. This is remarkable because these numbers, these ionization levels, are large numbers. They are of order 5 volt or 10 volt. And to line them up in such precise fashion to make a metal in a band structure scheme is rather remarkable and should be considered slightly unstable to certain perturbations. The other point is that we have low dimensionality. We have planes of copper-oxygen atoms, and we have chains of copper-oxygen atoms. We have nearly half-filled bands, and this adds all to instabilities. So we are close to instabilities. The type of instabilities that can occur, I will address them in the next two short contributions here, which are due to Werner Weber, who addressed the question of coupling to phonons, and to Chandra Varma, Stefan Schmidt-Rink, and Elihu Abrahams, who addressed the coupling to excitons. Now, Werner calculated phonons in these materials. In fact, if he uses the pure material, the material becomes unstable. So he has to dope it. If he dopes it, he moves the Fermi level slightly out of this perfect nesting condition, and he finds drastic phonon softening. If he does these calculations for all points in K-space and solves a Lierschberg equation, he can calculate Tc. And this is shown here as the yellow curve as a function of doping. And as you dope away out of the range where the material becomes unstable, you run into high Tc. It is unstable up here and over here, but as you dope out of this range, you run into high Tc of order 40 degrees for these materials. Werner is calculating at the moment the 90-degree materials, the electron-phonon coupling in these materials, and we'll see what happens. However, he has also realized that he is at the limit of what this theory can really support. the soft phonons that occur here have line widths, have lifetimes which are comparable to their frequencies. So the whole concept may become somewhat questionable, and maybe one has to go excuse me, into a more strong coupling limit or bipolar limit. The other picture, which is due to Chandra, and we change pace here somewhat, to Chandra Varma, Stefan, and Eliu, addresses this other type of instability that seems to be possible in these materials. I was already saying that the oxygen and copper levels line up, and one may actually have something like an ionic instability. The band structure gives the metal, but maybe this is just an accident. So maybe there are low-lying ionic excitations in the sense that one could create an electron-hole pair in the band structure, which costs you an enormous amount of energy of the order of several volts. But if you localize this enough in space, you can gain back this energy through Coulomb attraction. This is the idea of a excitonic instability. Having such a excitonic instability of strong enough oscillator strength, then you may use this exciton rather than a phonon to couple electron-hole pairs. This pairing mechanism has been proposed in the past. It leads to coupling constant and TC values which are characterized by this interaction. The fact that is somewhat different here is that in these materials, in contrast to what Little proposed in the past, the electrons that make the exciton and the electrons that get scattered off these excitons are basically the same electrons in these conducting sheets. Both models have to be tested. There are tests. For the phonon model, it would be to see whether the insulating material shows charge density wave type distortions. This model could be tested by looking at these excitons optically, by looking at low-energy electronic excitations. And this is being done by Joe Orenstein at Bell Laboratories, and he says he seems to see very unusual excitation spectra. Thank you very much.
Thank you, Michael. We have a 10-minute discussion period now, and actually we have the first question came from the corridor, and it was addressed to Phil Anderson. Perhaps you could respond to that, Phil.
It's a question from Mark Shorwin. It is UC Berkeley. To me, the first question was, how does the gap in our model vary with temperature? The second one was, would an optical measurement of the energy gap yield 2 delta or delta? I have to give two answers to that, depending on whether one is talking about the original Anderson-Bhaskar-Zoo theory or the new topological theory of the other heroes. The gap in our model works pretty much like a conventional BCS gap. The gap is probably rather large relative to KTC, and is probably extraordinarily anisotropic, so that there would not be a single gap in any case. It would be very, very, very anisotropic. But it would vary with temperature more or less according to the VCS theory. On the other hand, in the Kivelson et al. Theory, the gap is no longer a concept that is crucial to superconductivity. What gaps you see are different energies in this set of solitons, and one important such energy is the creation energy of a spin soliton, as well as the creation energy of a pair of whole solitons. The creation energy of a spin soliton is probably the gap that one sees in tunneling, and will not vary with temperature very much. It may not even be temperature, not even go to zero as you go to the transition temperature. As for an optical measurement, in the first theory you would have the standard optical measurement, the standard BCS theory. In the second theory, again, what optics will measure will be quite a different set of objects than those that are important in the condensation of the charges.
Thank you. Any other questions or remarks?
One question
Yes.
here. Timmy Data, University of South Carolina. The question is multi-parted because it addressed to various models. The model, what I will term the resonant valence theory, how critical are any one of these explanations? That means if one observes in a future superconductor, high-temperature superconductor, that R extrapolated to 0 degree Kelvin does not go to 0, how bad would that be for the model? Next question addressed to Van 't Hoff singularity and plasmon, etc. How anisotropic the macroscopic measurable quantities ought to be for these models to be viable. And finally, the AT&T model, what would happen if the KF1D and KF2D ratio are changed? Thank you.
The answer to my piece is I think it would be crucial for the soliton, for the charge E-soliton model, but not crucial, of course, for the other model, which looks much more like a conventional BCS.
I told that plasmon contribution can be determined experimentally from tunneling and neutron data, and when I should say that system I told is highly anisotropic, and in addition, because coherence length for this system is very small, it can be much smaller than mean free path, it can be even anisotropic energy gap or many gap situation, and that famous Anderson criteria can be met for such systems.
As to the third part of your question, the relationship is very critical. The position of the Fermi level with respect to the 2D band has been shown by Werner Weber to be very critical. In fact, I showed part of this here. With respect to the 1D band, it is still somewhat unclear because one-dimensional type instabilities seem to occur no matter where the Fermi level sits. However, the coupling probably will also be maximized if the Fermi level sits near the middle of the 1D band. So I think it will be very critical. The material seems to optimize itself by self-doping through these oxygen vacancies to sit somewhere where it couples strong enough to the 2D bands, but not too strong so it would become distorted in an insulator, and strong enough to the 1D band, so somewhere in between. The strongest coupling possible for the individual bands probably cannot be reached because they are shifted with respect to each other somewhat.
Art, did you want to make a remark?
Just wanted to comment that the position of the Fermi energy is rather crucial. It's determined in the lanthanum barium copper oxide case by the doping of the divalent ions up to about a doping composition of 0.2. There are almost no oxygen vacancies in that structure. In the case of the yttrium barium, the vacancies play a major role, and they will, of course, shift the Fermi energy from what has been calculated, and we think up to the peak that I showed you. In the calculation of Werner Weber, he unfortunately gets that the chi of Q is falling with increasing X instead of increasing as it should, because the density of states is going up. And that may be why he's getting, I think, on the curve you show that the T sub C is going down with increasing X for the lanthanum barium case instead of T sub C increasing with increasing X.
I think there's... Oh, yes.
Could I give an answer about the criticality of the Fermi level? In the RVB theory, the essential condition is that the Fermi level be close to half occupancy for all the coppers. And since we, of course, don't deal in terms of bands, we believe the system is basically a Mott insulator with doping. We don't assign a strict Fermi level.
Let's take a question way back in the room there. Way back there.
The Mike Yudkowsky, Northwestern University. I understand the tunneling measurements come up with one gap, and the far infrared measurements come up with a different gap. Perhaps I can tempt the theorists into leading the experimentalists to know whether this discrepancy in the gaps is real or imaginary.
See, who's that addressed to?
Maybe
anybody who wants to walk a limb.
I'll just say I'm very happy with it.
Okay. I think it can be explained, it has been explained by Cornell group, that this effect is connected with proximity effect. Because of proximity effect, you have two gaps, one major gap and second induced gap in the normal film, which became superconducting. And by infrared technique, you measure smallest gap. By tunneling technique, you can see everything. So because of it, if you have single crystal, you don't have such picture. But inhomogeneity can result in such situation.
Yes. Yeah.
Jose from Northeastern University. I have a question for Art Freeman. With regard to the lead, barium, copper oxide, do those materials have also the same properties as the lanthanum and the strontium and all the others? And if so, why is it that the lead, barium, copper oxide has such a low critical temperature? Or what determines the critical temperature? You said that most of these materials are analogous in the sense that they form layered structures. So the first question then is if the lead, barium, copper oxide is also a layered material.
You're talking about a lead, barium, copper oxide, but lead is divalent and barium is divalent, and he was talking about lead, barium, copper oxide. It's the first I know about that. I'm a little surprised because the lead is divalent and the barium is divalent, and you're just going to get an AbO3. Is that right?
No, but the experimentally said that all of these were the same family of materials.
I think there may be an answer to this, and this has to do with the fact that the lead probably does not dope on the barium sublattice, but on the copper sublattice. And if it does that, then it interferes directly with the electronic structure at the Fermi level. Remember, the Fermi level had copper-oxygen states. As long as you dope on the skeleton lattice, what I call the skeleton lattice, which is barium or yttrium or so, then you just throw electrons into the system. You may change the size and the pressure and so on, but you're not directly interfering with the electronic states.
Okay.
See, Phil? Can I ask a question of, I think it's Art and Michael. Serious question to me is that this phase transition, which takes place, the orthorhombic phase transition, in their theories is responsible for the insulating nature of the lanthanum copper oxide. But as far as I know, it was undiscovered in any resistivity data at any time. It has never been seen to be very strong in any resistivity data. It's very minor in susceptibility data. Why is it that this thing, which is supposed to be causing insulating character, is so electrically inactive?
We might hear from the argon group. They reported, in fact, that if you look at the resistivity, this is the lanthanum copper oxide, you lower the temperature and the resistivity goes way up. It looks very much like a semiconductor at low temperatures. The induced gap is small.
I think, Phil, to your question, if you take the band structure at face value, and I know you don't like to do that, then you realize that the distortions that are being observed there are these rotational distortions, and they do not couple to first order to the Fermi surface.
I know that.
This, you know that, not everybody else here on the table knows that, I think. This is an important fact. So from that point of view, one would have to argue on the basis of the band structure that these distortions are really coincidental and not the ones that couple, if there is an electron-phonon mechanism, the electrons. Okay? This is what I believe.
I'm very happy with that answer.
Okay, at that note then, we'll move on. Thank you very much.